Looking at the granite faces of the City of Rocks, evidence of 19th century overland migration is undeniable. Emigrants left obvious macro monuments marking their passage westward. Carved directly into the stone are specific dates, like June 12, 1850, that permanently anchor this location to the peak years of American expansion. This map details the California trail system. Notice how these separate, sprawling red routes stretching from the Missouri River converge into a tight geographical bottleneck here in southern Idaho. But away from the prominent rock faces, the landscape tells a different story. The millions of footsteps and heavy wagons that funneled through this corridor left marks on the earth that are microscopic compared to the granite carvings. What remains are swales, subtle, shallow depressions in the dirt and vegetation, compacted by the sheer weight of wagon traffic over a century ago. To the naked eye, these historic wagon swales look virtually identical to rutted two-track dirt roads carved by modern ranchers. Relying entirely on surface features to differentiate the two frequently leads to inaccurate historical mapping, as modern paths are routinely mistaken for historic trail segments. Because surface observation alone is an unreliable metric for cultural resource management, archaeologists must look below the topsoil to verify the true origin of a path. This aerial map shows the City of Rocks National Reserve. The 3 red markers represent survey locations conducted by the Midwest Archaeological Center. Archaeologists selected these sites because they contained surface linear features that were impossible to categorize by eye. The survey layout was strictly constrained by the local environment. High-density sagebrush and pinyon pine dictated exactly where researchers could physically operate their sensitive geophysical equipment. The study sought to answer a precise question. Can we identify distinct geophysical soil signatures that separate a historic trail from a modern road? Answering this necessitates non-intrusive prospection techniques, gathering accurate data through the soil profile without destroying the site through physical excavation. By defining clear soil signatures here, researchers generate a diagnostic template. That template can then be deployed to verify undocumented historic trails across the entire American West. To isolate the physical variable of the historic trail, the research team designed a tripartite survey, establishing 3 distinct testing sites for comparative analysis. The first testing area is the Pinnacle Pass survey area. This site represents the most complex variable in the study. Here, the documented historic trail and a modern ranch road physically overlap, blending their subsurface impacts together. The second testing area is the South Side survey area. This location isolates the first independent variable. It contains only the historic wagon trail, with no modern vehicular interference. The third and vital testing area is the quarry site. The quarry site isolates the second independent variable. It functions as the control group, containing a documented modern ranch road, but 0 historical trail traffic. At each location, the team laid out 20 by 20 meter rope grids, strictly aligning every transect line to magnetic north to ensure uniform data collection. Without the pure data from the quarry site acting as a control to define what a modern road actually looks like below ground, distinguishing the overlapping features back at Pinnacle Pass would be impossible. To read the soil profile, the team deployed 2 specific instruments. The first is an FM 256 fluxgate gradiometer. This device actively measures both the magnitude and the direction of magnetic fields generated by subsurface deposits. It operates with extreme sensitivity, capable of recording variations as minute as a single nanotesla. When the gradiometer passes over buried ferrous metal, it detects high-magnitude anomalies that warp the baseline magnetic field. The second instrument is the RM15 resistance meter. Utilizing a PA5 multi-probe array, the RM15 physically pushes a small electrical current through the ground to complete an artificial circuit. As the current travels, the instrument measures how specific soil horizons resist the electrical flow. The historical traffic of thousands of heavy overland wagons severely compacts the dirt. This alters the soil's capacity to retain moisture, which directly changes its electrical resistance profile. Running both magnetic and electrical prospection across identical grids provides overlapping datasets, increasing the statistical probability of identifying the subtle anthropogenic changes in the soil. When the team analyzed the data from the field, the results were stark. At both Pinnacle Pass and the South Side sites, the magnetometry survey failed entirely to locate the historic trail. The raw numerical data generated by the gradiometer was completely flooded with chaotic, high-magnitude frequency spikes. The archaeologists attempted 3 rigorous post-processing steps to salvage the data. First, they ran a zero-mean traverse calculation to remove heading errors. Second, they interpolated the x and y axes to mathematically smooth the visual representation. Finally, they applied a series of low-pass filters designed specifically to strip out high-frequency spatial anomalies. None of it worked. The algorithms passed over the corrupted data, but failed to flatten the spikes enough to reveal the subtle signature of the wagon ruts. The source of this catastrophic interference was simple: stray ferrous metal from modern barbed wire fences and scattered surface trash littered the sites. The intense, metallic noise of modern land use frequently drowns out the delicate signals left by the 19th century. Sensitive equipment alone cannot bypass a physically contaminated environment. But the magnetometry data from the quarry site control area told a different story. Here, operating in the complete absence of heavy ferrous contamination, the readings remained clean. This top-down grid visualization reveals a clear linear signature cutting directly through the eastern portion of the survey grid. Because we know exactly what occurred on the surface, we can correlate this subsurface feature strictly to the disturbance caused by modern ranch vehicles. This successful control validates the entire methodology. It proves that when properly isolated from environmental contamination, the instrument can successfully detect surface-level path disturbances. Placing the pristine signature of the control site directly against the corrupted data from the historic trail sites demonstrates the limitations of the technology. Returning to the initial research question, both historic wagon trails and modern ranch roads do leave distinct identifiable footprints below the earth. Heavy traffic permanently alters the localized soil profiles, particularly young mollysols, changing their physical properties in ways we can measure. The caveat is that these signatures are incredibly fragile and highly vulnerable to modern land use interference, like stray wire or trash. Confirming the exact route of a 150-year-old historic trail necessitates rigorous comparative site design to filter out modern background noise, a level of precision that sensitive field equipment alone cannot provide.